This is part 2, where we will be discussing random variables and random processes. Before we start, I really want you to think about your understanding, your current understanding of what a random variable is. I give a couple of options. Which is it? Think about it before we go into the module. You can pause and you can come back again. And hopefully, after this module, all of these concepts will be a lot clearer for you. So let's start. Given a measurable space, and remember, a measurable space is composed of two parts. One is the sample space omega, and the other one is the sigma algebra that tells us what is the structure of information that we are going to allow in the model. So given a measurable space, a function is called measurable with respect to the sigma algebra if this condition is satisfied. This condition is telling us for any interval from A to B, any interval in the reals, we are looking at the pre-image on omega that gives rise to the function f being inside that interval. And what we're asking ourselves is that contained in the sigma algebra? So basically we're asking, are the pre-images of this function events that are defined in the information structure? So what I'm going to do now is I'm going to take a little bit of time to visualize this concept, and for that I'm going to be sharing my iPad. So the visualization of measurability is the following. First of all, a mapping from the space omega that doesn't even need to be a numeric space, it can be anything, into the real. So these are the real numbers. So we have a mapping that takes elements omega in omega and assigns a real number to each of the outcomes, of the possible outcomes. So what we're asking for is, given an interval in the reals, we are asking for the pre-image omega such that the mapping is in this interval. So to begin with, when we talk about this, we're talking about pre-images. So we're talking about an interval here from A to B. And we're looking at what are the elements in omega that give rise to the function f being there. So this is what we call pre-image. So this will define a subset of omega. So this is a subset of omega. When we talk about the concept of measurability, I like to think about it in the following way. When we have a sigma algebra, an information structure, it is like a dictionary. It contains all events that are allowed in this model. So when we go back to the first example that we were looking at, it was Nicole and it was Dimas and it was Luz, and it was clear there that each one of the persons could be allowed to talk about certain events but not others, because they simply didn't have information about everything that was going on. So I like to think about the sigma algebra like containing all the events that are permissible in our model. So when we talk about measurability, we're basically going to be asking, is this subset a subset? So is this in our dictionary? And this is the main question. If all of these subsets, which are the pre-images, remember, it's the pre-images that are mapped into a particular interval, if all of these subsets are described in the sigma algebra, then we say that F is measurable with respect to the sigma algebra F. So we say that F is measurable with respect to the sigma algebra F. If the answer to this is yes. So let me go a little bit further and give a little bit of an example so that we can discuss this idea. Again, these examples are very simple, but I believe that they're quite pedagogical because they can help us visualize what we're talking about. So in this example, it's going to be really, really simple. This example, I'm considering omega to have only 10 elements. So I'm just going to name them up to 9. So there are 10 elements in omega, and I am going to consider a particular information structure. The information structure is going to be the empty set, the whole of omega, and it's going to have 2 sets which partition omega. A1 will be the even numbers, so it's going to be 0, 2, 4, 6, and 8. And A2 is the odd numbers. So again, we can think about visualizing omega as being this set. And this is a partition of omega. So defines a partition with 2 sets. It's the even numbers and the odd numbers. And as we have seen, very similar to what we've seen already, when we have just a binary model, which is this case because it's only a partition of 2 events, then the power set of the 2 events only has these 4 elements. So this is the sigma algebra that I'm going to be considering. So let's consider the function f1 of omega, which is defined as omega modulo 2. Basically, this function is a binary function. It has values in 0 or 1. And it will be value 0 for the even numbers, and it will be value 1 for the odd numbers. So it's a binary function, very simple. If we take a look at the pre-images, so the idea now is look at the pre-images in order to try to figure out if it's measurable with respect to the sigma algebra. Well, it's pretty clear that here, the pre-images of 0 are basically the set A1. So first of all, we want to compare with A and B. So I think about this in this way. This is a function that has values 0 and 1. So in order to actually apply the definition of measurability, we need to check for every interval in the reals that way. So think about like a ruler. If both A and B are to the left of 0, then this function doesn't have any values there. So the set omega such that f of omega is mapped there is the empty set. So if both are there, we map with the empty set, and the empty set is indeed in our sigma algebra. By the same token, if the whole interval is to the right of the number 1, again, there are no values such that the function f takes values beyond 1, and so that would also map into the nth set. Now, let's say that we have like a ruler here, and so we are going to slide the right hand between the numbers 0 and 1. So if we do that, then there is only one value of this function that is in this interval, which is the value 0. This value 0 is obtained only on the set A1. So this value 0 corresponds indeed to the set A1. And yes, it is there. Look, there it is. So indeed, in this case, we verify that the pre-image such that the value of the function f is in this particular interval would be a subset of the sigma algebra. So in this case, that would be that one. Now, let's consider, again, with the idea of the ruler, because the definition says that for all A and B, we need to verify that the pre-image, so all the omegas such that f of omega is in AB, is actually contained in, is an element of our sigma algebra. This is what we are verifying. So this is what we are verifying right now. So now let's continue. If now we are going to slide this, now we're going to put it this way. So we're going to put it in this part here, a little bit beyond. And I should probably erase this one because we've already done that. And we've already done this. So in this other case, for any number b that goes beyond 1, we have the pre-image of 0 and 1. Well, this function has only the values 0 and 1. So the pre-image of this set is actually the whole of omega. So the pre-image here is the whole of omega, because this function has values of 0, 1, and we're asking which are the elements in our sample space that give rise to this mapping being either 0 or 1. So we basically realize that all of them, all of omega, and all of omega is there. Yeah, it's there. We check that out. Now, we need to finalize by saying, all right, so we've taken into account all of the different possibilities except one. And the one remaining is if A is somewhere in between 0 and 1, and B is beyond 1, then the only value that that has is 1. The only way that F1 can be equal to 1 is when omega is an odd number. So that's exactly this set. And so we check that indeed that is A2. Because we have imagined this interval sliding along all the possible combinations in that contain 0 and 1, then we have verified indeed that this function is measurable with respect to this sigma algebra. Now, let's suppose that we have a function f2, and this function is the function 2 times omega. So is this function measurable with respect to this sigma algebra? In order to, in this case it won't be, in order to realize that this is not the case, I'm going to use an example. I'm going to ask what would be the particular case, all the omegas such that f of omega is less or equal to, say, 6. Well, clearly, because f of omega now is just 2 times omega, clearly this gives me the set This is equal to the set 0, 1, 2, and 3. And this is indeed a subset of omega. But this subset of omega is, I'm gonna draw it now with another color. Say I'm gonna draw it with a yellow color. So this subset is actually this subset here. And this subset is not contained in our sigma algebra, because our sigma algebra doesn't contain the intersections between the A1 and A2 partitions. So for this particular case, we conclude that this function is not measurable with respect to the sigma algebra that we have. I do want to make a remark because this is going to be important. And this remark is the following. Particularly when we're working with countable spaces omega, finite omegas and uncountable, the remark is the following. If we consider a sigma algebra F as the power set of omega, then what happens? In this case, it contains all of the subsets. Are in, say, our dictionary. So when this is the largest sigma algebra that we have for a set omega, so we are considering that as our dictionary. It says, you know, we can speak anything. We can talk about any possible event. Then all the mappings are measurable. And this is going to be important because it's perhaps one of the assumptions that is most common when you're looking at elementary courses in probability. They usually consider that if you have a set omega, then you're going to have all of the events. You can talk about all the events. You can have all the events in your information structure. But in advanced courses, and even in the example of Luz and Dimas and Nicole, we can pretty much see that when you do have complex situations, for example, sensors that are placed in a city and they are looking at different parts of the information that the city is giving you, then at that moment, you cannot get away with the fact that each of the sensors is going to have a different information stream. So let's go back now to the slides. Now, suppose that we have a measurable function. If we have a measurable space, then a function x is called a random variable if it is measurable with respect to the sigma algebra. So that is the actual definition of a random variable, not just the function, but it has to be a measurable function. So in order to define a random variable, we need the elements of omega together with the information structure. Furthermore, the sigma algebra generated by a random variable is the smallest sigma algebra with respect to which x is measurable. And in the same way, we can define the sigma algebra generated by 2 random variables, or 3, or 4, and so on. In order to visualize the sigma algebra generated by a random variable, what we can do is a constructive way of doing it, is to look at the partitions that are induced by the random variable in the case that this is a discrete random variable. And so we look at the partitions and we realize that those partitions are the main events that this random variable can actually identify. Let's take a look at an example, again, going back to our iPad. And we're going to go back to the example of the nickel and the dime. So in this example, we're going to define the nickel and we're going to define first some functions, because the outcomes, heads of the nickel, heads of the dime, are not real numbers. So now I'm going to define this. Xn will be the number of heads for the nickel. Now clearly this is the binary random variable, because nickel is just tossing the coin once. So it's either 0 or 1. And the same way, when Dimas tosses the dime, we either have 0 heads for the dime or 1 head for the dime. Furthermore, we are going to define XL as being XN plus XD. So it's the total number of heads in the experiment. So now the important thing is, how do we build the sigma algebra generated by Xn? And of course here, I'd like you to guess what this is going to be, because we've already encountered this sigma algebra. So how do we build the sigma algebra generated by Xn? First of all, if we consider the sigma algebra F as being the power set of all omega, it contains all of the subsets of omega. And so these two functions are functions from omega into the reals, because they have binary values, and they would be random variables with respect to the largest sigma algebra, which is the one that contains all of the events, that is all of the subsets of omega. So how do we build the sigma algebra generated by Xn? Well, we take a look at the pre-images. So these will be omega 1, omega 2, omega 3, and omega 4. And we ask ourselves, when is Xn equal to 0? So, well, to be precise, because we tend to do shorthand, but to be precise, what are the sets omega such that Xn of omega is equal to 0? Well, omega 1 is heads on the nickel and heads on the dime. So definitely omega 1 is part of the pre-image of this set. So omega 1 is contained in this set. The omega 2 was heads on the nickel and tails on the dime. So again, omega 2 is also contained in this set. But omega 3 and omega 4 were the two elements where the nickels come out tails. So for omega 3 and omega 4, Xn is equal to 0. Oh, sorry. I was sorry. So I'm doing when this is equal to 1. Sorry about that. So this is equal to 1. So this is exactly equal to omega 1 and omega 2. And similarly, the set omega such that Xn of omega is equal to 0 will be the set omega 3 and omega 4. And that's all we have, because X cannot have, the mapping cannot have any other values. So this is when we realize that the mapping X is creating a partition, which of course we have already encountered before. So this creates a partition into the two sets. This is the set that we had called Hn, and this is the set that we had called Tn, and it's a partition of omega. So the sigma algebra generated by the nickel will be nothing but the sigma algebra that we have already defined in the previous part on this, the previous module for this class, as the sigma algebra for unique. And that is a constructive way to look at the sigma algebras generated by random variables. So now, as an exercise, I've done Nicole. So now I'm asking you to do the sigma algebra generated by DMAS, which should be pretty straightforward, and then build the sigma algebra generated by both random variables xn and xd. And please compare with the sigma algebra generated by xl. And the other question is, how is xl, which is a number, related to the light color that Luz will be seeing? Again, you can pause now the video and try to answer these questions, or you can finish the module and answer the questions later on. Given a filtration, given a filtration on omega, a stochastic process is now a collection of random variables such that for each time index t, xt is measurable with respect to the sigma algebra ft. So this is also called adapted to the filtration. We say that this is a stochastic process that is adapted to this filtration. Now, the special case when the filtration is the sigma algebra generated by the process itself, it's important here that we take the sigma algebra that is generated by the random variables xs for all time s smaller or equal to t. When we take that into account to build the filtration, it's an increasing sequence of sigma algebras or information structures, and this is called the natural filtration of the process. Because it contains all the information from the past, it is common in engineering and other disciplines such as physics and chemistry to refer to the natural filtration as the history of the process up to time t. And this is something that you will see very commonly done. So they refer to f of t as the history of the process up to time t. Finally, a random stopping time. So when we have a process, a stochastic process, a random stopping time adapted to the filtration f is a random variable tau such that the following condition is satisfied. For every time t, the event that this stopping time has arrived, that you can see that it has actually ended, is in our dictionary. It is in the sigma algebra f of t. So you can pretty much realize that this is contained in the information structure. And that's what is the random stopping time. So we're going to see an example. In this example, we go back to the game of craps. How do we build a stochastic process? For the game of craps, we're building the stochastic process as follows. We let x of t be the outcome of the two dice at stage t in the game. X of t clearly has real values. It can have any value, integer values, between 2 and 12. So first of all, we realize, or we should remark, that the filtration is built gradually. So for our first random variable, so when we take into account time t equals 0, so for t equals 0, we have the first random variable x0. is just simply the outcome of the throw of two dice. So for this random variable, we have the information structure, the natural, the sigma algebra generated by this random variable is simply the power set of the set from 2 to 12. So it's the power set of this set, which we can call omega 0 if you want. Once we have stage 1, so we know that the first x0 was in the continuing set, then we form the sigma algebra by taking into account the first random variable and the second random variable. Now, the second random variable is again a random variable that depends only on this omega from 2 to 12. And so we start building the information structure, or the filtration, little by little. So in this case, we have a stochastic process, xt, with the natural filtration, which is, as I explained, the filtration or the information structure that is built adding one more throw of the dice every time, every stage. So how do we define the end of the game? Well, we say the game is going to finish. The total number of stages in the game is either 1, because you just did the initial step, if your first random variable is either in the losing part or in the winning part. So if you lose or win on the first draw, on the first throw of the dice, then you only played one stage. Otherwise, if the x0 is in the continuation space, then tau will be the first time when x of t is equal to x0, or x, in which case you win, or x of t is equal to 7, in which case we lose. So that is the definition of the number of stages in the game, and it is a random stopping time, because for any time t, the event is tau equals to t, is t the end of the game, it is observable. It is inside our information structure, because it only depends on the values that we have seen of the throw of the dice up to time t. It is defined in terms of the minimum over the trajectory, and so it depends directly on these random variables. So this is an example of a random stopping time for the game of craps. And the second example that we're going to discuss is the following. In this example, we are looking at a subway station that has trains. This is going to be something that, well, actually, I did use it for my research, and I have programmed these kind of things, and it is very common to do this in simulations. So you have a subway station, and let's say that we call time t equals 0 the moment that the station opens to the public, and the duration of the whole day will be capital D. So the station closes when we come to capital T. We denote it by Ti the inter-arrival times of the trains, which is a random process. And An will be the arrival epoch of train number N. That is, An is basically just the sum of all the inter-arrival times. And we define tau as the total number of trains in the day. Now, I'm going to show you the iPad so that we can have a little bit of a visual for this. So the visual for this is the following. We have a train station. So, I'm sorry, I wanted to do it in black. So I'm going to be using black. I think it's better. You can see it better. So the TIs are basically the inter-arrival times. So let's take a look at that in this way. Let's say that, well, this is the opening time, so this will be t equals 0. Let's say that the first train came at this time. So the time between these two is t1. Let's say that the second train arrives here. So t2 is the time between the second and the first one. Let's say that the third train comes in here, so that would be t3, and so on. So the arrival time of train J is the sum from I equals 1 up to J of Ti. So this is the arrival time of train 3. This is the arrival time of the second train. This is the arrival time of the first one. And we just define A0 as being the initial time 0. So tau is defined as the first time maximum t such that A of t is less or equal to d. Let's say that the end of the day is here. So this is t equals 0, and this is t equals b. In this example, we might say that, there's 3 trains in the day. That's what I drew in here. Now, we're going to build this as a stochastic process. So how do we do it? Our basic variables, if you think about simulating this like a computer scientist, you would be generating the inter-arrival times. So that's basically what we call the underlying process or observation. So we build the process starting out, building it up from T. So we call FT the sigma algebra generated by the random variables T1, T2 up to T of little t. So this will be the natural filtration of the arrival process. A very interesting observation is the following. If we now consider the process of the actual arrival epochs, A, J, is adapted to the filtration. Why is that adapted to the filtration? Because AJ depends only on the previous values of T. So the information that we have from T1 up to T sub T is going to be, the information that we have in here is going to define uniquely the value of AT because it's just the sum of them. So AT is measurable with respect to the sigma algebra generated by T1 up to TT. So basically what we have is that AT is FT measured. And what we are asking now is a random stop in time. So the question for you would be, so this is basically what we have. And now as an exercise for you, you will be asked to determine if this is a random stop in time. So this is the picture, and we go back to the slides. So your exercise is to answer the following. In this example of the trains, is tau a random stopping time? And the next question is tau plus 1 a random stopping time? There is an important remark before we finish this module. We have defined random variables and processes, and we haven't talked about a probability yet. These lectures are called probability theory, and yet we haven't used the word probability a single time. It is not needed. This is an important remark because this is going to be very important very relevant when we work in financial mathematics or when we work in simulation. Because in both cases, we can use methods that are called changes of measure approaches. And these methods, whether theoretical or practical, are going to have a huge influence in the models that we have. So indeed, in order to define random variables, we don't need to define a probability. This is actually what we're going to do next. So in our next module, we're going to see probability measures and probability distributions. Thank you.